Okay, so we have a short little unit here on probability and counting. And counting comes up in probability when we're thinking about probabilities as frequencies. And so we've kind of been doing this throughout the course. We think of frequencies as ratios, the ratios of the number of ways that something can happen that we're interested in divided by the total number of possibilities. So let's kind of look at that more systematically. If we're thinking about random draw with equally likely outcomes. And let me just make a comment on that phrase. When we say we choose something at random, we usually, in context, that usually means that all of the outcomes are equally likely. Like if we choose a person at random from a group, the idea is that each person has an equal chance of being selected. So if there's n people in the group, the probability that each one is selected is 1 over n. Slightly different use of random is in random variable. In random variable, there's no implied equality of probabilities. But when we talk about choosing something at random, that's usually what we mean. And in that case, the probability of an event E is the number of outcomes in that event, E divided by the number of outcomes in the sample space. So we've been doing this all along. So for example, if we have a group of 50 people, 30 are registered voters, then the probability of selecting a registered voter is 30, the number in the group divided by the size of the group, 0.6. Okay, again, nothing new here. We really have been doing this, but what I'm kind of setting up for us to do here is I'm drawing your attention to the number of times that we need to count things to calculate our probabilities. Okay, so this is something that only applies to the kind of random variables where we can count the outcomes. So only applies to discrete random variables, but it applies often enough that it's worth talking a little bit about. And in particular, it's worth going through a few formulas that help us count things in scenarios that arise over and over again, where the counting gets a little bit tricky. Okay, so I'm going to go through a few formulas in this lesson and the next one that will just kind of add to your set of strategies that you can use to find probabilities. Okay, so let's start a fresh page here. And let's talk about what's called the counting principle, if we're going to give it a name. Okay, so let's just start with an example here. Let's say we have a ballot, and it's a ballot from a state like California where we vote on particular policies on ballot initiatives. And so let's say we have a ballot with 4 propositions. Okay. And for each of them, the outcome can be, you can vote for it, you can vote against it, or you can abstain. You can just leave it blank, okay? There are 3 possible outcomes on each item. Okay, so the counting principle gives us the answer to the question, how many different ways are there to cast this ballot? Okay, how many different possible combinations of yes, no, and abstain would we have with these 4 items, each of which can take 3 values? So let's just think it through. Well, there's 3 possibilities for the first. You could yes, no, or abstain. 3 for the second, 3 for the third, and 3 for the fourth. Okay, so it's 3 to the 4th power. And that doing an example with fairly low numbers helps us sort of see the logic of a broader formula. Okay, so the broader, we call the counting principle. I'm going to use the language that Bertsekas and Tsitsiklis use, thinking about the outcomes as outcomes of an experiment, which is, I don't know, I have mixed feelings about it. It's a little bit weird, but it's kind of weird in a helpful way, so we're just going to use it here. If we have M experiments, each of which can come out in different ways, the total number of outcomes is n to the mth power. So the counting principle is, in one sense, it's like the definition of multiplication, practically. It's like, what do we mean? There's 3 different ways for the first one times 3 different ways for the next one. It's really, in one sense, quite clear, but can get a little bit hard to apply. And I think one place where it gets complicated is just trying to figure out, okay, so which one is M and which one is N? I think the best way to approach that, if you find yourself being confused, is to start to write it out, to start to go through this kind of process that I just went through. And so, okay, so for the first item, it can come out 3 different ways. And so right away, if you ask yourself, how many ways can the first item come out? That's going to tell you that's going to be your N here. And how many terms are there going to be in this product? That's going to be the number of experiments. So let's kind of annotate that here. So each factor is the number of outcomes for the first experiment, the first initiative, the first thing, whatever it is. And then the number of, that's an individual factor. That's what number we're multiplying the others by. And then the number of factors here is the number of experiments. Okay. And so this is kind of one version of the counting principle where each of the experiments has the same number of outcomes, but it's also, they don't have to all be the same. Okay, if we have still having M experiments. Okay, so if we're thinking about a ballot, M things to vote on, and each experiment, let's have a variable to talk about which experiment. Each experiment I has n sub I possible outcomes. So for example, we could have yes, no, abstain on the first item, and then we could be voting for one of 4 candidates, and then we could maybe have just a yes, no with no abstention there. We would have 3 times 4 times 2. The logic is still the same. We take the number of possible outcomes for each individual item and multiply them together until we've taken care of the whole number of items. So just writing that. If we have M experiments, each experiment I has n sub I possible outcomes. The total number of outcomes is n1 times n2 times n3, all the way up to n sub n. So what we've got here are the number of possible ways the first item can come out, the number of possible ways the second one can come out, the third, however many there are. Okay, so this second version is kind of the most general one. The first is a special case to some extent of it. We might, if we wanted to even write this product down here, we could use the product symbol if we wanted to. If it's confusing, there's nothing wrong with the way I've got it written right now, but just reminding you that that's the same thing that we could write as the product as I goes from 1 to m of n sub I. Okay, so there's one way to kind of systematically count things that we will run into over and over again. Another kind of question that arises a lot is how many different ways there are to order things. Okay, and so this question, we call that a permutation. Each different way of ranking a set of things is a permutation of it. So for example, if we're thinking that we have 3 candidates, oh, let's call them A, B, and C. How many different ways are there to rank 3 items? Ways to rank them, to order them, rank order them. We could say it all those are synonymous ways of saying the same thing. So we'll just call them A, B, and C. A perfectly fine way to approach this, and it is strongly recommended. Strongly recommended as a starting point when the numbers are small. If the numbers aren't small, pick some small numbers and take it as a starting point anyway, is just to list them, just enumerate them, just make the problem concrete. These counting problems get tricky when you try to do it all with variables and all abstractly in your head. The way to get comfortable with that is being more concrete. So you're asking me, well, how many ways can I rank A, B, and C? Well, watch me do it. So one possibility is just the way I wrote them. Okay, so A, B, and C, that's one way. A is my first choice, B is my second, C is my third. Here's another way that has A as a first choice, but now I've got C as a second and B as a third. So those are the only ways I can do it with A being a first choice. Let's think about B being a first choice. So I can have B first, then A, then C, and I can have B first, then C, then A. And that's all the possibilities with B. And so I can have C first, then I can have A, then I can have B, I can have C first, I can have B, and I can have A, and now I'm done. Okay, and that is the correct answer. Okay, there are 6 possible ways to order 3 items. So that works when the numbers are small. Of course, when the numbers get bigger, you might not want to do that, or you might not trust yourself to be able to do it right. But you'll notice I was doing it in kind of a systematic way. And so let me talk you through the logic of the formula for a permutation here. All right, so, and we're going to go in steps. So if we have 3 items, there were 3 choices for first place. Okay, it's like I'm choosing first place first, and it can be A, it can be B, it can be C. Once I choose first place, there's only 2 possibilities left for second place. Okay, so then there's 2 choices for second place. So once I've got A as my first choice, it's either going to be B or C. And then once I've got my second choice, there's really no more choices left. Okay, whatever's left is third, and that's just that. If we want to say it in a sort of a parallel structure, we might say that there's just one choice for third place. And now we're going to use that counting principle. This is our quote unquote experiment with 3 possible outcomes. The first, top of the ranking. The second experiment is the 2 choices for second place, and the third experiment isn't really much of an experiment at all, because whatever hasn't been ranked yet is going to be third place. Okay. So what we have here is 3 possibilities for the first place, times 2 for the second, times 1 for the third. And if we had a bigger number, what about n items? It's the same deal. There's n possibilities. Each one of those n items could be ranked first. Given that, then there's n minus 1 left for the second one, for the second place. So we've got our first place chosen, we've got our second place chosen. Now we're trying to figure out what's in third place. Well, we've got n minus 2 left for that. And you're starting to see the pattern here, all the way down to, for each successive place, we've got 1 fewer items to choose from until we have step n, which would be 1 choice for last place. Okay. So this is what about, my missing word here. So if I want to write that systematically, the total outcomes, then I'm just going to apply the counting principle the same way I did in this example with 3 choices. But here I've got n possible ways to pick the first place in the ranking, times n minus 1 for the second, times n minus 2, times n minus 3, dot, dot, dot. You get the picture. Then I'm down to 2, then I'm down to 1. Okay, so this expression where you take an integer, a positive integer, and you multiply it by each of the integers smaller than it, we write this as n with an exclamation point. And you don't say that n, you say it n factorial. And that is indeed the number of permutations of n items. And that is the answer to the question of how many ways are there to rank n items. Okay. Start with n, that's a positive integer. If we're counting things where you're getting a positive integer, right? And multiply it by every positive integer that is smaller. So if the, use a different color and see if I got a little bit of space here. Let's say we had 7 items. The possible ways of ranking them would be 7 factorial, and that would just be 7 times 6 times 5 times 4 times 3 times 2 times 1. You don't really, never really need the 1 in there, but I don't know. It appeals to people's sense of tidiness, mine included, put it in there. So n factorial, number of permutations, we'll be using that in another formula in the next lesson. So I'll see you then.